The first talk is remote. It's called Boundary Tree with multiple context-free grammars and downwards closures.
Yeah, hi everyone. Thanks for coming, and sorry that I couldn't be there in person. Yeah, as I said, I'm going to talk about bounded Treewidth systems, about multiple context-free grammars, and how to compute downward closures for these systems. I'm Schütze. This is joint work with Aiswarya, with Pascal, Baumann, with Prakash, Saivasan, and Georg Zetzsche. And I just kind of want to set the scene by taking an example. So imagine you're given some kind of complicated system. For example, an operating system. And on that operating system, you have programs that are running. And nowadays, these programs are probably multi-threaded, so they have several threads, each with their own processes, with their own stacks. And over the course of the execution of that program, you will probably switch back and forth between these threads with their stacks. And then occasionally, the operating system will say, okay, different program now, and swap in, give priority to a different program. Again, separate set of threads, separate set of stacks. And this program will switch back and forth. Maybe we go back to the previous program. Maybe the user starts a new program. And now you have this really complicated system of interacting processes. And you would like to answer the big question, can the system reach some kind of undesirable state? For example, some kind of error state. And so if you just look at this, you might see immediately that this is undecidable in its full generality. Because even if you just had a single program with two stacks, it could already simulate a Turing machine, and then it's undecidable. So there's a couple of things we can do. So first of all, we bound the number of times that any given program by itself can switch between its stacks. And that is already sufficient to make the individual processes decidable. And then we will also compute the downward closure of the language of the whole system, which is basically possible because irrelevant spawns of programs that are never executed can be ignored. And that makes the analysis task as a whole feasible. So what are these downward closures? Okay, so imagine you're given some word, and now you can define an ordering between words. We call this a subword ordering, and basically the idea is that one word is smaller than another word if there is some kind of scattered embedding from the letters of one word to the letters of the other word. So pats embeds into parrots, so does art, so does pot. And then you get this whole set of words that are smaller than parrots, and that is a downward closure of parrots. And of course, we can then extend that to a whole language. Why do we like downward closures? Well, there's a long-standing result that tells us no matter what your original language is, the downward closure is always regular. And of course, if you have a regular language, then a lot of tasks become either feasible in the first place or much more efficient. Okay, so if we go back to our original example, we decided to make this task feasible by bounding the number of context switches, but that's not the only thing we can do. We could also instead bound the height of each stack, or the number of times that each stack can kind of reverse the direction, so switch between pushes and pops. And all of these bounds might seem a bit arbitrary, but in practice we have seen that even for small bounds, we can already detect a lot of relevant bugs in practice. But there's a bit of a problem to this because there's always these different bounds you can take. For each of these bounds, essentially, you have to find a new algorithm to compute the downward closure. And this is kind of where our contribution comes in. So we're starting with these systems that are all bounds on multi-stack automata. And there's a long-standing result or a sequence of results from literature that tell us that these are all equivalent to some model called bounded Treewidth, which I will explain in just a bit. And then our contribution is that we show that this is equivalent to another model called multiple context-free grammars. We do this other translation because it's a bit easier for our purposes to analyze. And then we show that if you have these multiple context-free grammars, you can find a succinct construction for the downward closure. Okay, so there's two systems here that I'd like to introduce in a bit more detail: bounded Treewidth systems, multiple context-free grammars. For the bounded Treewidth systems, imagine we're given a really simple system that has access to two stacks. So the system can push and pop A's from one stack, and it can push and pop B's from the other stack. And now we're looking in more detail at one specific execution of that system. So we might start by pushing an A on one stack and push a B on the other stack. And you can see at the bottom, I'm starting to draw this linear graph, which is basically just a sequence of the steps of this execution. Might push another A, might push a B. Okay, and now we have popped a B that we have previously pushed. And in our execution graph at the bottom, we add an arc to kind of pair these two states. State 1, where the B was pushed, and the state 3, where the B was popped. And then we continue. We push a B again. We pop an A. So we draw an arc again. We pop another A. We draw another arc. We pop the last B and draw the last arc. And let's say that is our execution. And now we have this run graph at the bottom, this execution graph. And of course, as for any graph, you can find a tree decomposition for that graph. And that kind of already gives you a flavor of what we're looking at. We're saying a language has K bounded Treewidth if there is some formula in MSO logic that defines a set of run graphs, and the set of run graphs that the subset of those run graphs that have Treewidth K is exactly the language we're looking for. Okay, so that's a bounded Treewidth language. And then the other model we were talking about were multiple context-free grammars. So a normal context-free grammar, we probably all know, you have this set of non-terminals, you have some terminals, and the non-terminals can derive sequences of terminals or non-terminals. And then multiple context-free grammars kind of generalize this by asking, okay, what if we add multiple registers to each of these non-terminals? So each of these registers can now contain its own word, and these are kind of derived jointly. So you can see the S terminal, the S non-terminal, that still only has one register. A and B both have two registers. And these rules now not only tell us which non-terminal go to which non-terminal, but also how to rearrange the registers. So you can see the S rule, for example, tells us, okay, if I have an A with registers X1 and X2, I can concatenate the contents of these registers with some separator symbol. Or alternatively, the B non-terminal I can always construct with a single B in each register just from nothing. You can see that I draw these arrows the other way around. That's just, I think, notationally, because I think it's a bit easier to think about multiple context-free grammars as being built up from the bottom up instead of derived from the top down, but really it's equivalent. Okay, here's the derivation tree of a multiple context-free grammar. You can see it looks exactly like a normal derivation tree, except we're writing down all the contents of all the registers at each step. And these are strictly more powerful than normal context-free grammars. For example, we can derive these copy words, which are just a word and then the word repeated, which a normal context-free grammar cannot. One second. Okay, I want to give just a brief overview of how we show that these two systems are equivalent. Don't get too hung up on this because I'm going to skim over it fairly quickly because I want to talk more about the downward closure. But just to give you a hint. So we start with a bounded Treewidth language. So this consists of bounded Treewidth run graphs. And then we can show that we can find a tree automaton for these run graphs that accepts these run graphs. And then from a tree automaton, it's fairly simple to construct a multiple context-free grammar. And in the other direction, we start from the derivation trees. We add some edges that basically tell us where one component, where one register starts and where it ends. And then we can show that these graphs that that result from that are in fact MSO definable. Just a brief overview. If you want to have more detail, either find me afterwards or read our paper. The other thing that I want to talk about, obviously, is how to find succinct construction for the downward closure. And I think for that, it's helpful to consider how we construct downward closures for normal context-free grammars. This is a long-standing result from Corcel. It's called Corcel's construction. The idea is that if you have a really simple grammar like this, for example, and you have any tree that is sufficiently long, then you will have a path in that tree that repeats some non-terminal several times. And if you have that repetition of a non-terminal, that means you can either cut it out entirely or you can repeat it multiple times. And for the purposes of the downward closure, that means that you really just need to look at the alphabet that is produced alongside that loop of non-terminals, because obviously the order now doesn't, for the downward closure, the order really doesn't matter because you can repeat this as many times as you need and then drop all of the letters that are not in the order that you want. So we just look at the alphabet and we repeat this alphabet as many times as we'd like. And so we introduce these rules that are called accelerated productions because in some sense they allow us to do multiple derivation steps in one single transition. Yeah. So in some sense, we'd like to apply this construction directly to multiple context-free grammars. But these several registers that these multiple context-free grammars have, they give us some challenges. So first of all, in a multiple context-free grammar, it's possible that only individual components, individual registers are acceleratable. As an example, if we have a derivation tree like this, you can see that in the first component of the D's or the S's, you can kind of accelerate these A's because you can produce arbitrarily many A's. But if you look at the second register, you can't really accelerate the second register. It will only ever contain a single letter. And even if you can identify kind of which components, which registers are acceleratable, you can in fact shuffle these around. So you also need to be aware that potentially something that is acceleratable in one component might be acceleratable in another component later on. And lastly, even if you have done all this work to identify which components are acceleratable, you can't just ignore the other components because there might be dependencies. So here's an example. I have two derivation trees for the D non-terminal. And you can see on the left, this is acceleratable because I can have as many A's as I'd like. And on the D, this is not acceleratable. It ends after one step. So I know that I can accelerate in the first component. I can put as many A's as I want to. But there's a dependency here that tells us, okay, if I accelerate in the first component, then my second component must contain a B because the transition that puts a C in the second component will not lead to a derivation tree that is acceleratable. Okay, so how do we approach this? First, we want to identify which components are acceleratable. And here is some derivation tree. And now I'm gonna kind of draw these connections between the non-terminals in a bit more detail by looking exactly at which components go to which components. This we call an embedding map between the non-terminals. And so we can see, okay, from the S to the C, X and Y both go into the first component, Z goes to the second component. We can continue this up to the A non-terminal and then continue this up to the S non-terminal. And the point is that we are looking for these embedding maps between non-terminals that are idempotent. Why are we looking for idempotent embeddings? It's because remember that Corcel's construction relied on the fact that you can essentially repeat a loop as many times as you would like. And if we have an idempotent embedding, then this means that this function, this embedding, will always be the same, no matter how many times we repeat this loop. And so the fixed points of this embedding is exactly where we will accelerate. because everything will flow into the sides from these into these registers. Okay, so we know where we want to accelerate. We don't really know what to put into these accelerated components. For this, I'm going back to this derivation tree and imagine, okay, now we're looking at just the fixed points of these embeddings. So the X and the Z, because that ends up in the first and the third component respectively in the top. And now let's look at the D on the right, for example. We can see that the D, the first D of that D non-terminal, that kind of joins the X in the C non-terminal, and it joins from the right. Imagine this kind of as a river. The fixed point of the embedding from X to X, that is kind of the main river, and then there's little letters flowing in from the side. So we can see that D ends up in the first component, and in particular, it gets concatenated to X from the right. So this is our alphabet sigma 1 right, of all the letters that can occur on the right. Similarly, the other D can join Z from the left, so it's in sigma 3 left. And that kind of tells us what our alphabets are. Okay, so now we just need to figure out how to deal with these dependent components. And I'm going to show you next a very complicated derivation tree, but don't worry, we'll simplify it in just a second. So again, we start by identifying the fixed point of our embedding from the S to the S. Everything else from the S component at the bottom flows into the first component. And now we want to accelerate this register at the top. So we introduce these alphabets, sigma 1 left, sigma 1 right. We take them to the cleanest star because we're accelerating. And then we are introducing a new non-terminal for now on the left. That is just basically the S from the bottom, but we just restrict it to the first component. And we do that because essentially what we'd like to do in the end is cut out everything in between. So this kind of helps us shorten our derivation tree in the end. And then we are, okay, we have now this accelerated register at the top. And we can see that the B non-terminal, its first register is now irrelevant, right? Because it's already subsumed by these watershed alphabets. So we can essentially ignore the first register. And so we introduce a stack-rated version of the non-terminal that tells us, oh, we only care about the second register now. And the same thing happens here with the A non-terminal. But here we need to be a bit more careful, right? Because here we see, okay, there is actually a dependency here because that D, that is the third component of the A, that only can, that might be a dependency, right? Because it tells us this D can occur because it is occurring on that path from S to S with the embedding we're looking for. And so we can't just project the other two away. We still need to make sure that we are only taking the appropriate derivations. So what we're doing is we are annotating this non-terminal with the target non-terminal and with the embedding that we'd like to guarantee. And we continue this process going down to B. We can now see, I mean, B is essentially empty at this point because all of its components end up in the watershed. And but it's just here to kind of verify that we find the correct S in non-terminal. And we go down to S, which embeds into itself with the identity mapping. Okay, and then we're done. And you can see that this non-terminal, this derivation tree is now much simpler than the one we started with, and it's shorter, which is the important bit. So I've shown you kind of how to take a multiple context free grammar and how to shorten it. And if you have a sufficiently short automata, if you have a sufficiently short tree, you can just write down an automaton for it. But I kind of promised you some kind of succinctness. So how small do these trees really get? Okay, so imagine you're given some kind of derivation tree. And now we pick out any path in that derivation tree. And if that path is sufficiently long, then we know we have some kind of non-terminal type that gets repeated over and over. And we can write down the embedding maps between these non-terminals. And now there's a result from Ramsey that tells us if that graph of the same non-terminal type and its embedding maps, if that graph is long enough, if it is big enough, then there must exist one clique that is monocolored. And monocolored here means obviously, because the colors are our embedding maps, this means that the embedding from the bottom to the middle and from the middle to the top and from the bottom to the top are the same. Well, that means that this must be an idempotent embedding, right? Well, but then this is the point where we can do our shortening procedure that I described earlier and cut out everything between the top and the bottom non-terminal, and that shortens our tree. And Ramsey's theorem tells us that this essentially is a constant. It's not a constant in the number of registers of the grammar, but because we're always talking about bounded trio systems, we can assume that the number of registers is constant, and so the whole tree height just becomes polynomial in the number of steps. Thanks, I'm almost done. Okay, so just to recap, we have shown that bounded tree systems are multiple context-free grammars. We have used these embedding maps to identify the points in the derivation trees where we can accelerate productions. We can use decorations to ensure that the non-accelerated components have all of the dependencies satisfied. And we can bound the maximum height of these derivation trees via Ramsey's theorem. Yeah, and this is the end of my presentation. Thanks for listening. If you have any questions, I'm happy to take them now.
So does the tree width appear as some parameter of the multiple context-free grammar? For
yes.
example,
it's not a one-to-one correspondence, but it roughly corresponds to the number of registers in the grammar.
would be
here, for example,
the maximum arity of any non-terminal?
Exactly. Yes, that's correct.
See. And when you do the translation from MCFGs to the tree width, is that the maximum tree width that you get?
Yes. Again, it's not one-to-one, but they're in some linear correspondence to each other.
Okay. And do you have some optimality around that?
No, I don't think we looked at the optimality of that.
Okay, thank you.
No, I don't think so.
Let's thank the speaker again and move on to the next talk.